Okay, today, folks, we're going to talk about curve sketching, section 3.5. Actually, curve sketching is a culmination of all the topics we talked about so far in chapter 3. I'm off my numbers. I'm a math teacher. I'm not supposed to be on all the time. So anyway, you get the idea. Involving the first derivative, involving the second derivative, as well as finding critical points, minimum, relative min, and relative max. It combines everything together. So let's look at the following. All right, now, oftentimes, a graph of rational functions may display a different type of asymptote. This is called an oblique or slant asymptote. So, you're used to asymptotes being either vertical or horizontal. Well, in some cases, they're not. It's a diagonal line that serves as a barrier guiding the end behavior of the function. Okay, now, I'm going to show you in just a moment, but when I divide the function, and you'll see it right here, the equation for the slant asymptote is y equals 3x plus 4. If you look at the graph, it's kind of an approximation right there. So right about there. That's pretty much the equation y equals 3x plus 4. It doesn't look like it on the graph the way the numbers are, but you get the idea of how it works. Now, the thing to remember is it's only the non-remainder portion. So that's this part right there. When we divide it, you're going to get 3x plus 4. It doesn't matter what the remainder is. It's just going to be that part right there. And the rational functions, the degree cannot exceed the denominator in order to have an oblique asymptote. All right, so now let's look at the following function. We got x squared minus 2x plus 4 all divided by x minus 2. So when I determine what the slant asymptote is going to be, it's going to be the function y equals x, because when I divide this, I get x. But I have a remainder of 4. But remember, the remainder doesn't matter. It's just the quotient part, the non-remainder, which is x. And when I graph this function, now mind you, this is a very rough sketch, so it's not exact. But if you type this into your graphic calculator, you're going to see what's in green. Well, the blue part is the slant asymptote. So I went ahead and I labeled it right there. And then this function right here is that and that right there. So actually, I'll just erase that. So there we go. Okay. But you get the idea. All right. So you got that. So that kind of comes from 3.2. Okay. Now, so far we've studied several concepts. We've already talked about some of this stuff. I think I talked about this with 3.2. I don't remember right off the bat, but you get all this information. You can read the equations for vertical asymptotes, intervals of increasing and decreasing by the first derivative method, and then intervals for concavity as determined by the second derivative test. So we've done the first derivative test to determine whether it's increasing or decreasing, and also help us to determine whether it is a relative minimum, relative maximum. We've done the second derivative test, which determines concavity, whether it's concave up or it's concave down. All right. Now, here are some guidelines for determining the good viewing of the graph of the function. First, determine the domain and the range of the function. Okay, that's pretty straightforward. You've been doing that anyway. Then, determine the intercepts, asymptotes, the symmetry of the graph. Then, locate the values of x for which f prime and f double prime are 0 or do not exist. Use the results to determine the relative extrema, the minimum and maximum, as well as the points of inflection. And that also include, when I said relative min or relative maximum, that's the critical points. So the first derivative will determine the critical points, and the second derivative will determine the points of inflection. All right, now, here's what we have right here. I went ahead and just giving you the results, because we could spend 15, 20 minutes just determining the first derivative and second derivative. You know how to do that by now. So here's the equation. F of x equals, here's its first derivative, and here's its second derivative right there. Okay, now, here's what you need to know from this. You need to know that To sketch this, and I got this right here, the x-intercepts are going to be at -3 and 0. So the vertical asymptotes are at x equals 2 and x equals -2 because right here, x squared minus 4, remember, x squared minus 4 is x plus 2x minus 2. So that's how you get 2 and -2. And you get a horizontal asymptote at y equals 2. All right. So the domain is all real numbers with the exception of 2 and -2 because those are vertical asymptotes. And then the test intervals will be from, and this is where you get it. So vertical asymptotes right there. So it's going to be from, the critical number is 0. The reason the critical number is 0 is because of right here, 20 times x. Well, if you set 20x equal to 0, then x has to be 0. So that is a critical number, and there are no points of inflection here because if you set any one of those equal to 0, you're not going to get that. So, all right. So, with that being said, this leads me to right here. We got our equation. We got our first derivative. We got our second derivative. Okay. Now, we have from negative infinity to positive 2. F prime is positive when we test value. F double prime is also positive. Now, if F prime I meant negative. I apologize. It's negative. F prime is negative. That means the function's decreasing. If F double prime is negative, then that means it's concave downward. And we'll analyze that here in just a minute. Okay. At x equals -2, they're all undefined, so it's a vertical asymptote. And we can check that by plugging it into any one of those functions, and that will be the case. You will get 0. All right, so from -2 to 0, f prime is negative, which means it's decreasing, and then f prime double prime is positive, which means it's concave upward, which we'll talk about that in a minute. All right, so x equals 0, that ends up being a relative min. Why? Because it goes from, f prime goes from negative to positive, so therefore that's why it's our relative minimum. All right, now, from 0 to -2, f prime is positive, f double prime is positive, therefore it's increasing and it's concave upward. And then finally, I don't like orange. I know you all know that by now, but I'm telling you again anyway. So, all right, from 2 into infinity, f prime is positive and f double prime is negative. Therefore, it's increasing and it's concave downward. And we can check all this information right over here. So, from negative infinity to -2, decreasing, which this function isn't decreasing, and as you can see, it's concave downward. So therefore, we can check that off. Okay, so check. Check right there. Okay. Now, from -2 to 0, it says it's decreasing, which that is true, and it's concave upward. So, yes, that is true. Check. From 0 to 2, it's increasing and it's concave upward. So that is true. So I check that off. And then finally, from 2 to infinity, it's increasing, which you see here, and it is concave downward. So that is true. So check. All right. All right, so you see all those things are true. That's by applying the first derivative test and then the second derivative test and coming up with test values in those ranges. So your test values here might want to be, like say, -3, -1, 1, and +3. Or you can use anything in those ranges. It's entirely up to you. All right, now, be sure you understand all the implications of creating a table such as shown here, but by using calculus, you can be sure that the graph has no relative extrema points or inflection points other than those shown in the figure. The graph of the rational function having no common factors and whose denominator is 1 or greater has a slant asymptote when the degree of the numerator exceeds the degree of the denominator by exactly 1. So, and the only time we saw that earlier, right there, this was the second degree, this was the first degree. So when you have a degree of exactly 1, that's what happens. Same thing goes with this first one we did. So those are things you got to look at there. All right, now this was not a very long lesson because it's a compilation of all the stuff you've done already in this chapter, but all the stuff comes together. It's about creating a table. Now with this, it says on here there's a website. It actually says a worksheet. I have posted a worksheet on Canvas. There are 4 different curves and tables to create. I only want you to do 3 of them. If you want to do all 4, I tell you what, if you want to do all 4, I'll throw in 1 or 2 extra bonus points on it for you. But you only have to do 3 of them. And it's entirely up to you which ones you do. You can work them by yourself, or you can work them with a partner. I'd rather you work with a partner virtually or work apart. However you want to do it, that's fine, but I'll let you do that. You have until Tuesday, December 1st, because of the holiday. I'm giving you a couple extra days to work on it, but you must send it to me, and it must be all handwritten because you got graphs, and then just like in before, take a photo of it and then send it to me that way. So, all right, that's all I have for you. So we'll sign off.